Hello, my name is Bayerlein. I'm professor at Technische Hochschule Lübeck, and I want to introduce in my simulation program RegC. This program is developed in Fachhochschule Lübeck and comes with some functions which I want to display in my presentation. First, this simulation program works with a signal block diagram editor, and this editor can be filled with up to 70 analog blocks like PT1, PI, and so on. You can investigate open loop and closed loop programs. So for control systems, this is ideally suitable. It can have up to 10 open inputs. And the three main tasks, the three main jobs of this program is you can calculate step responses, Bode plots, and with the same information polar plots. And furthermore, this program can calculate parameters of PIDT1 controllers with the Bode plot design method, well known as FRA, as frequency response approach. The purpose is this program should support students in the control system lecture at Technische Hochschule Lübeck. Is developed since the last 30 years and adapted to today's needs. It should be easy to use, so the introduction you see here takes not less than 30 minutes. It is simple to install. The program itself includes the zip file is less than 300 kilobytes. No installation is necessary. And furthermore, it comes with no fee, no cost. You can have a free download, and it is open source, written in C#, my favorite programming language, developed with Visual Studio. And maybe if you want to change something, you can look into the source code and change for your needs. You can find it either in the Lernraum in the Technische Hochschule Lübeck, in the course Toolprogramme Bayerlein, or if you are not member of Fachhochschule, you can find it on my homepage, 3xw.jörgbayerlein.de. There you have to go to menu Projekte, then C# projects, and then RegC. And there you can find, or you can directly go to the page 154. The demonstration includes, of course, the presentation of the program itself. First, I want to show how to build up a simple example with a PI controller and 2 PT1 closed loop system to show you how to easily calculate the reference step response of this loop. With given numbers here, this is an example from a lecture of mine where I demonstrate the PI function. Then I give you some hints to work with the signal block diagram editor. And furthermore, finally, I want to close with the more complex example which I use in my control system lecture. You can find this example with complete design methods in my workbook. See on my homepage in this menu point Beruf, and then go to control system lecture. Then open the workbook and start with page 36, and then you can find this loop with 4 PT1s, a designable controller, feedback loop, and then I show you just the design of a PIDT1 controller, and finally the reference step response of the designed closed loop system. Okay, let's start. I open the program, and you see it opens with German text. If you want to have English text, very easy, click on this US flag button, and then all comments and words and menu points are changed into English language. The back to German is not prepared. To build up a signal block diagram, you can find here a list of blocks, standard control system blocks like P, I block, differentiator, PT1, DT1, PI, PD block or PT2 block with damping smaller 1, delay time block, polynomial function, and so on. Then to draw a signal block diagram, you need branches, summing points, and minus signs. And these branches can be activated with this button, summing point with this button, minus sign with this button. If you click on it, then with the cursor you can place this signs. And if you want to have a block, for example, I want to start with the EBA, click on this block, move the mouse without pressed button, just click one time, click a second time to put it on your screen, and then the program asks for the parameters. So I type in the parameters. K should be 2 and time constant should be 1. This is the parameters of my loop. I show you, I close this button and I show you the total loop. Here I have the picture of my desired loop. So this controller is now a fixed PI controller. If you want to go back into the parameter box, just put your mouse on the block and press the right mouse button, then you get the parameter menu window again. Note that here is a transfer function and here's a limit value, which is very large, but each block includes also a limitation. Say OK, then we put the next 3 blocks at PT1. Say here, PT1 should have the gain 0.3175, should have the time constant 1 second and no limitation. It is a very large limitation. Note that in this program the decimal separator can be a point, dot, or a comma. So it is independent of your setting in your computer. This program accepts both decimal separators without any problem. Say OK. Second PT1 block with the block gain 1 and the time constant 0.6. I make this 0.6. Yeah, you see, I take a dot here. We can make a comma, so this doesn't matter. Say OK, and finally we have a delay time block. That is this block with a delay time of 1.3. Okay, now the blocks are prepared. Now I can close the loop. So what we can do is first we click on branches to draw branches. If I click this button, you see here we are now in the mode to draw branches. That means I can now make any number of branches I want to have. So I make the following. I make here a branch, second branch. So with a mouse click first, I define the starting point. With the second click, I define the ending point. Start, end, start, end, start, end, start, end, start, end, start, end, start, end. You see, with some exercise, you can very easily set up the signal block diagram. Now I need a summing point. The summing point can be located to this type of connection of branches. You see the branch drawing mode still is open until you click another button. If you want to have a minus sign, click on this button and look for a branch. Go with your mouse, peek on a branch, click on that branch, and then the branch gets this minus sign, which means the signal is inverted. So that's all. This is a plan, and now I can show you how it is easy to draw now a step response. Here I want to apply a unit step function, and I want to measure the response here, the closed loop reference step response. I click on the step response button, then the step response window is opened. You see here some parameters you have to set. First, the time range. I have looked for a time range of 10 seconds. Step amplitude should be 1 unit step amplitude. The output number must be defined. The program can calculate any number of any output of any block. I want to see the output of block number 4. Here you see that is the output of my closed loop system. Here you can define the input number. If you have only one input, you see the input is numbered automatically, starting with 71. 70 blocks, 10 outputs are possible. So there is no other input number possible. If I click on recalc button, then the step response is calculated. You see the graphical display. So after 4 to 5 seconds, we reach the maximum, and after 6-7 seconds, the output settled to the final desired value 1. You see, this is a typical reference step response of a well-designed closed loop system. So far, some hints. If I close this window, still in the background available. Now some hints to draw the plan. I have introduced these both buttons. If I draw a branch at that point, you see the button is still active. So this takes so long as I click either a summing point button or a minus sign button or this pointer button. Pointer button means if I look on it, now I'm the pointer mode. That means now I can select branches and blocks again. And for example, I select this branch and click the delete button on my keyboard, and then this parts can be deleted very easily. I of course can open with the press mouse button a rectangular field. All elements in this field are selected, and if I click on the delete button, also parts of my signal block diagram can be deleted. Now of course I want to show you another thing. I'm in the branch mode. What is not allowed is that a branch starts with on another branch. Then you get a message that it is not allowed, because this means this must be a junction point. If you need a junction point, there is no other way as to delete this line. I select the long line. If I want to have a branch there, I have to delete this. Then I have to draw 2 branches. The program needs this connection point. Then you can make this as a junction point here. So I think very simple. The same as the summing point. You can locate a summing point here, but this doesn't work because the summing point needs the ending of a branch at the summing point. So I delete the summing point, I delete this line, and this is the working plan. So I can show you now the Bode plot function of this program. For example, if I want to have the open loop Bode plot for controller design, this is necessary. Then I first remove the feedback. I mark the feedback lines and click on Bode plot. In the Bode plot window, again, the program asks for starting of the radian frequency value on the right side of the the left side of the Bode plot. You have to define the block output. Here I want to see, of course, the output of my 4-block system, and the input 71 is also be defined. If I have only one input, you can only select this value. Then you can select if you want to see the only the magnitude, only the phase, or both magnitude and phase, or the polar plot. I want to show you, I think the best is magnitude and phase curve. In total, if I click on recalculate, then you see the Bode plot. If you want to see the, you see now the display doesn't fit to my screen. These are the omega values. You see 1, 2, 3, 4, 5 decades. If you have fine lines, a minor grid line, you can here see more lines, so that this indicates a logarithmic scaling. Here you see this is a phase curve. This is wrapped in the range 180 to minus 180, so this comes from the delay time block, of course. This is the magnitude. Blue curve is magnitude, red curve is phase. So this is the open loop Bode plot of my system. On the right side here you have the degree scaling. Here's the dB, decibel grading scaling of my loop, and this is the radian frequency omega. So far, I close this loop, and of course with these both buttons you can load a signal block diagram, or here you can store a complete signal block diagram and load it for later purpose. Okay, next example. The next example was my 4PT1 loop. Note that, and I want to show you how to design a PIDT1 controller. Note that these blocks cannot only be theoretical blocks. There are possibilities here in this list where you can load a measured Bode plot or a measured step response, so you can really design real systems with measured data. But so far, for the first introduction, I showed you this loop. So the theory behind it and the theory to design this controller is described in my workbook. I mentioned this in my PowerPoint presentation. Now I set this up. First point is I need the designable controller. This is the block RegC from the German Regler. I put this block on the screen, and here you can see the parameters of this block fits to a PIDT1 system with the first the settling time Tn, the differentiation time Tv, and the high frequency gain increase step called step depths. So step depths, D time constant, Pi time constant, and proportional gain are the 4 parameters with the system. Also here you can set a limit, and these parameters I leave unchanged because these are coming out of my controller design method. So I close this box and finalize now my plan. I show you the numbers. First I need 4 PT1s with gain 1 and time constant 0.01. Second PI with time constant 1. Third PT1 with gain 2 and 0.05. And finally a fourth PT1 with gain 1 and time constant 0.33. Okay, there is a P block in the background. Why not should I do this? I put here a P block. The gain is 1, so this has really no effect, but I of course can do the job. Then we have 2 summing points. I click on the summing point number, set this here, and there is a summing point at the output for disturbance. you see I can only draw one summing point. If I want to have a second one, I have to push second time the summing point button. The same as with the minus sign. After drawing of one minus sign, this is automatically deactivated. The only button which stays until you stop it with this button is the branch mode. I think now I can go into the branch mode. Click on this, start and start and start, and I think you hear the clicking. Start and start, and of course you can draw this, doesn't matter anyway. Here you see automatically, if you define the branch, the input on the right side, automatically then the left side is the output. So both the blocks can be used in any direction. This is a summing point with one input, one output, so no effect. But if I want to have a disturbance input, I have to do this, and I have a second open input. I can deactivate the branch mode with the pointer mode. Now I can check, okay, is it all? No, I have a minus sign here. So I click on the minus sign button. We need a negative feedback, of course. Otherwise this cannot be a stable loop. All parameters now are set. If I want to check the parameters, I can click on each button with the right mouse button and reopen the block. But there is a button here which displays all parameters in one display. Here are the number of the blocks, type of the blocks, gain of the blocks, time constant of the blocks, and other parameters. And so this gives an overview about your total block system. Now I want to start the controller design method. The theory behind it I cannot explain here in my presentation. Just look and feel what happens with the controller design method. First, I start it. Then the program asks for two parameters. The starting omega, because I need the Bode plot design. Of course, then the Bode plot left starting point must be defined. 0.1 is mostly a good value. And the program analyzes the structure of the loop and find out that the block number 6 output is the feedback line for controller number 1. I design block number 1. The program also can design more than one controller. We say OK. And now you have to decide if you want to have a differentiating part or a pure PI controller. Of course, I want to have a PIDT1 controller. Then you have to define two parameters. First, the time constant of the controller and the step depth of the controller. I just take a value of a step depth of 10. This is an example in my workbook. The time constant now can be selected. The program makes a proposal defined with a -30 dB method. But of course, you can select the second largest time constant. I think with this button, I copy the proposal into the active field. This is a number the program internally really needs. So I used. So I say OK, and now the next parameters comes with for the PI block. The phase margin is the stability indicator, and the larger the value, the more the system is damped. 60-degree phase margin is a typical value. This is the value the program uses, but this is the value the program proposes, calculated with the -12 dB over decade gradient method. Internally, I accept the proposal and just go out with the PIDT1 button. Behind this program now, the open loop Bode plot is analyzed. The phase margin value is used to define the crossover frequency. Here you see the 0 value is the base information about the stability. Here you see the 60-degree phase, -120 is automatically settled, and if I close this border plot window with the close button, I get the resulting PIDT1 parameters. So the program calculates a crossover frequency of nearly 5 per second. The controller gain is 2.81, and these are the both proposed time constant values with the method of pole compensation. This is the step depth value. And if I close the program a second time, this window a second time, the values are stored in my controller. And you see, if I open the controller block, here all values are copied into this controller. I close this function, and I finally want to show you that this controller is well designed. I click on calculate the step response. I delete this curve from the last example and recalculate now the block number. Delete this window, block number. I want to see the output of block number 5 and input number 71. You see, I show you now the 2-second display of my program. The phase margin of 60 degrees gives a small overshoot, less than 10% overshoot. The final value settles at 1. So this is the PIDT1 reference step response of my 4PT1 system. So far, I hope you see that it's very easy to use, fast calculation for the main points used in designing single loop systems. I wish you a good get into this operating mode, get into the using of this program. Be happy to have this for free. I would be glad if you work with this program in your control system practice. Thank you for your attention.